Previously, we were looking at confidence intervals, and we made some remarks about what controls the size of a confidence interval, and sample size was one of those, that you can narrow a confidence interval if you increase the sample size and hold the confidence level the same. It's that concept that we want to pursue. If we just look at the confidence interval formula for estimating a population mean, we have the population mean plus or minus a critical value times the standard error. Okay, this part, it says let E be equal to this part over here. All right, so that's our E, or error of estimation, also known as, may refer to it as a margin of error. Okay, the magnitude of E, or this bound on the estimation, is changed by selecting the different confidence interval or changing the sample size. Okay, so we know if we change alpha, Z changes, that changes the magnitude of that, but I don't want to sacrifice confidence. So I want to maintain a high confidence level. So if I want to decrease decrease a confidence interval, I want to do it by increasing sample size, not by sacrificing confidence, right? I want to keep confidence high. Okay, so we know those two things influence it. So suppose we fix the confidence level, all right, and then we take this expression and we solve it for n. So as we know what the margin of error, say we want our margin of error to be within a specified number of units, and we want to maintain a specific confidence level. And the only thing we don't know then is sample size n. Okay, how big does n have to be? So we just take that expression up here for margin of error or error of estimation, and we solve for n. So we have z squared, that's from the table, sample variance divided by this bound on the error or error of estimation, margin of error, whatever you want to call it. If we solve for the sample size by this above formula, that says that our interval will be our sample mean. Goodness, that didn't make sense. The sample size determined by the above formula implies y bar will be within E units of the population mean mu 100% of the time. 1 minus alpha times 100% of the time. Okay. The problem with this formula is, okay, this is determined solely by confidence level. This is determined by the bound on the error or margin of error. That's determined by application or the researcher. How do we determine sample size? How do we determine sample variance if we don't have a sample? Right? If we're trying to decide on what the sample size is, but if we don't have a sample to compute sample variance, how do we do that? Okay, so if no sample has been selected, then we know this value of S or S squared is unknown. Okay, there's a couple things we can do. If we can use prior information about sigma if it's available. So suppose you've done some kind of a pilot study and you get some estimate of variance, then use it. Okay, what if you don't have that? So that's in some of the researchers that I'm working with now, they're saying we want to be able to control this margin of error. We need to be this. We want to know our estimate is within a specified number of units. Okay, how big a sample do I need to do that? I'll say, well, have you done any work with this before? Can you give me some information on how variable that population is? Well, we haven't taken any measures yet. Or, yeah, we did a little trial run with a small sample, and we've got this estimate of variance. Okay, and that may be all I have. Okay, the other thing you know is that if we call the empirical rule. Okay, the empirical rule, if you know your data are symmetrically distributed or kind of mound-shaped distribution. Okay, if you have that information, you can use that because the empirical rule says what? you have a mound-shaped distribution that if you go forward 1 standard deviation, backward 1 standard deviation, you have approximately 68%, right? If you go forward 2 standard deviations, backward 2 standard deviations, what's this area going to be? It's approximately 0.95 or 95%. Okay, and you could go out 3 and capture almost everything. Okay, so if you know that you have a mound-shaped distribution, you can use the empirical rule. The range of the data would be all, if you did all or almost all of the data, so from 3 standard deviations away up to 3, you're breaking this up into pieces. Okay, so you could use range over 6, saying this standard deviation 1, 2, 3, 4, 5, 6. All right, the range divided by 6 would estimate sigma. That actually is not as good an estimator as range over 4. That 4 comes from the fact that 95% of your data are within 1, 2, 3, 4 standard deviations. So range, that's where that comes from. So recall the empirical rule. And sometimes that may be all you have. Okay, so let's look at an illustration. Ten years ago, the average undergraduate student loan borrowed $9,750 in student loans. The variance of the loan totals was $10,240,000. That's variance. That seems large, but remember it's in squared units. Okay. Now, present day, how many students' loan information is necessary to estimate the average student indebtedness to within $1,000 with 95% confidence? Okay. So this question then, we want to estimate the student indebtedness to within this $1,000. That is, we want our error of estimation be 1,000. We want to do this with 95% confidence. So 1 minus alpha is 0.95. What we have is from 10 years ago, this variability information. So we're going to use then our current variance. We're going to assume a similar variability and say sigma squared is approximately 10,240,000. All right, so if we want to find out what n is, or how big a sample we should take present day, we need our formula here. Okay, so we want to look up a z-score that determines a right-hand area of what? If 1 minus alpha is 0.95, alpha is 0.05. So therefore alpha over 2 is 0.025. And we're squaring that quantity. S squared, we're going to use this previous value that we have available, divided by the error of estimation is 1,000, and that must be squared also. The critical value for z is what? We've seen that one a few times already. 1.96? Yes? If you need to look it up, that's okay. I don't want to square the variance, otherwise I'm going to really be thrown off. So be attentive. Do you have standard deviation? Do you have variance? Because if you square something when you shouldn't, or vice versa, you could really have some problems. So what is the sample size that we get? 39.3380. Okay, sample size, always round up. You can't take and sample 33% of a student's record. You either get it all or you don't, right? Okay, so always round up. So we need at least 40. Student financial records. Must be sampled. Make sense? If you rounded down to 39, you don't achieve 95% confidence. So you know you'll get at least 95% if you go up, round up. So that's why we always round up. Now what could change? What could change is the variance that you get today versus what happened 10 years ago. The variance could be different, but we don't know that. We need to start somewhere. So that's assuming a variability like we saw 10 years ago, we need the sample of size 40. How can you change the sample size? What happens if you say, I want to know within a smaller value of E, bound on the error of estimation, that's smaller than 1,000. What's that going to do to sample size? If E gets smaller, that's this denominator, N gets larger. Okay, so the narrower the interval, you need a larger sample size, right? Okay, so to that end here, what if we wish to estimate the mean indebtedness to within $500? How many students are necessary? Or how many records are necessary? So what changes then is our E is equal to 500. We're still going to keep our alpha at 0.05, and we're still going to use our 10 million figure for the estimated variance. So we know we still have 1.96 squared times 10,240,000. This time we're dividing by 500 squared. Have 157.3519. So that means at least 158 student records. Must be sampled. Okay, always round up. Notice what happened there. The bound on the error was cut in half. What happened to the sample size requirement? It goes up by a factor of 4, a power of 2, right? So what we could say here, here E decreases by half and increases 4 times. Now we don't see the factor of 4 after we round, but when we look at these two before we round, that's certainly 4. Okay. what happens if our, and it makes sense that it should. So in general, if your error of estimation decreases, your sample size should increase, right? If you want to have a narrower interval, you've got to have a larger sample size to do that. So typically this formula is used whenever large samples are available and achievable, okay? And so that if you go through and you think, well, perhaps in this student loan situation, suppose you wanted a sample size, or pardon me, an error of estimation of 100, okay? And then you compute your sample size that's required for that, and it's just huge. Okay, there's no way I can get that many. Or whenever you're looking at outside of this particular illustration, suppose you know for each sample item, each object that you collect for your sample, there's a cost attached to that, right? Your time, equipment, money, you know, there's cost attached to everything you measure. Okay, so that's one of the reasons we want to ask this question then, is if I want to be this close, how many do I need? Okay, so suppose you go through this and you find out that for your experiments you need a sample of over 1,000, and it takes you a week to run one. You're never going to graduate, right? You didn't want to hear that. Okay, it's like I can never graduate. And if I have to run 1,000 of these, and it's going to take 1,000 weeks worth of work, I'm never going to get done. Okay, so perhaps your choice of E was too small. Okay, so then you have to rethink it. Well, maybe I don't need my error of estimation to be that small. Okay. Or you know there's a dollar figure attached to those. Maybe you can get them done quickly, but each one of them is going to have a huge dollar figure attached to it that you have to buy materials for. It's like the project can't afford that. So there's some things you have to do before just jumping in and starting the experiment. How close, what information has been available in the past, and can I use that to make some decisions about sample sizes I choose now? Okay, I want to make an informed decision. I don't want to just blindly go ahead and hope I have enough, right? Okay, so I want to make some informed decisions about sample size. So suppose you go through all of this and you have one of these, you have costly subjects in your experiment, all right? Your budget just doesn't allow for these really large samples. So even you may have a sample of size 50, which for the student records thing isn't a big deal. But if you're looking at, you need a tree to measure something on, you need to destroy 50 trees or animals or whatever the case may be. And it's like, that's just not feasible. I can't do that. Okay, so this large sample, this works for when large samples are feasible. Okay, and that's usually when you see the sample size determination. But if you're in an area where large samples aren't feasible, okay, I can only deal with small samples. Right? What do I do in that case? All right. So that's where we're headed next then, is what if I don't have a large sample? Because our testing procedure, our confidence interval, and the sample size determination all said large samples were feasible. For the testing and the confidence interval, it says I had a large sample in order to use those Z-scores, right? That's because that meant the central limit theorem was working. All right. So what happens if I have a small sample? What are some examples of things that would require a small sample? All right, suppose you're dealing with AIDS patients or anyone who's ill. All right, small numbers are what you have, and in some of those cases, small numbers are what you hope for. You don't want, so that's all you have. Okay, or it's very costly. You're in an engineering process and you're working with a metal alloy, and it costs over $1,000 per unit. It's like, I don't have the budget to do 50 of those. I have a budget to do 8. Okay, now can I still test those hypotheses? Can I still compute confidence intervals? Or am I just out of luck because I have a small sample? All right, so the answer is yes, you can still do stuff. You can still You can still do hypothesis testing. You can still look at confidence intervals, but because you don't have a large sample, we've got to change our approach. Okay, we can't use standard normal scores anymore because central limit theorem isn't backing us up anymore. Okay, I've got to change my approach. Okay, and that's where we pick up next time.